In this lecture, we're going to talk about super-resolution microscopy and F techniques. So in the previous lecture, we know that light microscope has limited resolution. For example, for fluorescence microscopy, the resolution could be given by the Abbe resolution limit formula. So we can see from this formula, which we have known in the previous lecture, the resolution of microscope is dictated by the wavelength lambda and objective NA, numerical aperture. For our current technology, the Abbe resolution limit has been so well educated among physicists and microscopists. The microscope NA for a very long time, about 1.4, very little effort spent. So therefore, our resolution on how to break the resolution limit would only reach about 200 nanometer. So in the recent decade, that's why we say that light microscope has a resolution about 200 nanometer that could afford our light microscopes with resolution better than 200 nanometers. So these light microscopes are called super resolution microscopes because they can afford resolution more than 200 nanometers. They can break the Abbe resolution limit. So for these super resolution microscopes, they could be characterized by two different methods. The first method is engineered PSF method. So for this microscope, the PSF is made to be smaller. So we know that PSF determines the microscope's resolution. So the larger the PSF, the lower the resolution of microscope. So if we can make a microscope that has smaller PSF, of course, we could have a super resolution microscope. So this is not the focus of today's lecture. So today, we're going to focus on single molecule localization approach to achieve super resolution microscopy. So for single molecule localization based super resolution microscopy still uses conventional hardware configuration of light microscope. So that means the microscope essentially has the same PSF because it uses conventional hardware configuration, the same NA and the same wavelength. However, the super resolution is achieved by using Gaussian fitting or center of mass. Previously, I have talked about it is possible to use conventional microscopy to observe single molecule. The single molecules, their images in the conventional microscope essentially just a dot. So to be exactly, their image is the PSF in 3-dimensional, or in 2-dimensionally, it appears at area disk. So here is a GAP single molecules observed through a conventional light microscope. So these single molecules, you can imagine that they are undergoing Brownian motion, so they move very fast. So in order for us to see it, we have to find a way to immobilize single molecules under glass cover slips or using other methods to immobilize it to some other substrate surface. So you can see the single molecules, these images, they appear. The fluorescence appears and then immediately disappears. So it looks like they are blinking. But eventually, after a long time, you can see that the fluorescence particles are less and less, and eventually most of them are photo-bleached here. So the single molecule fluorescence displays all or none property. So if we observe a single molecule fluorescence, and we plot its intensity as y-axis. So this is intensity of single molecules, and this is this is the time or frame number of this particular single molecule. We can see that its fluorescence intensity remains the same at the beginning, and suddenly, within instant time, it lost its fluorescence intensity. Now this intensity is about 0, is about background fluorescence intensity. So we call it, this is all or none property of single molecule fluorescence. So this fluctuation is because the noise. So this is all the background noise. So the reason why single molecules have all non-fluorescence property is because single molecules, their fluorescence is based on single molecule fluorescence. So once this molecule is photobleached or destroyed, of course there will be totally no fluorescence. Now let's look at a very simple case to illustrate how does single molecule based super resolution microscopy work. So imagine we have a fluorescent single molecule. So here it is. There's only one single molecule here. Now we know its image is the PSF in 3D, and in 2D is the area pattern, or just to be approximation, it is the area disk. So here is this image, area disk. So the resolution is limited by the size of area disk, and area disk is very large, much larger than the single molecule size. So, but it's very easy to imagine that the single molecule's position, although we cannot directly see it, but we know that the single molecule must be the center of this area disk. So this is not so difficult to imagine. So, but the problem here, the area disk is not a simple geometric circle. It's inhomogeneous. We know that the center is brighter and the periphery is dimmer. So there are two mathematical methods to figure out the exact center of the area disk. So they are the Gaussian fitting or center of mass method. So let's look at a Gaussian fitting. So we know that a single molecule image in 3D is a PSF, the American football size shape. Well, in a 2D, in a CCD membrane chip, it projects as an area disk. So this is the image of the area disk, so it's highly pixelized. We could use two-dimensional or 2D Gaussian function to fit the distribution of this area disk intensity. So after this fitting, so this is a 2D Gaussian fitting, we can work out the center peak. We can work out its x position and y position. Therefore, the Gaussian center represents the position of single molecules at nanometer resolution. So now let's look at center of mass. This is an alternative approach to figure out the center of area disk. So center of mass is a concept from the physics. So in the physics, center of mass refers to the point as if all the mass of the object is concentrated there. So I suggest students can go back to review the concept of the center of mass. So imagine that a PSF is a real object. It has a mass, and its mass is equivalent to the fluorescence intensity. Then the center of fluorescence mass, or just in short, center of mass, represents the precise localization of the single molecule. So let's look at the example here. So this is the fluorescence image of single molecule. Let's assume this is the image, and the background here is all 0, and here there's 3 pixels, and each pixel has exactly the same intensity value. So you can imagine that the center of mass will be around here. So you just imagine this is an object, this is another object, and they together form an object. The center of mass should be here. The coordinates of center of mass could be worked out by using the following formulas. So this is the x coordinate of the center of mass is equal to each pixel's x coordinate multiply each pixel's intensity and sigma means sum up all of this together and divided by the sum up of all the pixels intensity. So this will give the x coordinates of the center of mass, and similarly we can work out the y coordinate of the center of mass. So the center of mass method would give us also super resolution localization of single molecules. So both Gaussian center and center of mass give very similar localization results for sub-pixel precision. So this will afford the conventional microscope with super resolution. For single molecule localization microscopy, the precision is represented by sigma. So sigma here represents the standard deviation. So here is the sigma. The sigma is proportional to the inverse square root of n. So n here represents the number of photons collected. So from this formula we can see that if we increase the number of photons collected, the sigma or standard deviation will become smaller and smaller. If we could increase the collection of photons to infinity, then the precision of single molecule based localization microscopy will be indefinite. The sigma will be approaching zero as well. So this is the most beautiful and amazing things for single molecule based localization microscopy. So if we can collect sufficient number of photons, if your signal is single molecules are sufficiently bright, so we can reach as high precision as we will want. We can reach nanometer, we can reach even sub-nanometer or even angstrom precision. Why more photons results in more precision? So analogy from the shooting game could help us to understand the reason why. So let's assume that there's a match between a professional and an amateur. So the professional has only one bullet given. So here is a professional result. Okay, so it's really not bad result. It's very near to the center of the bull's eye. So now let's look at an amateur. So the amateur has been generously given 3 bullets. So here is the result. So you can see the result looks very pathetic. So none of them is even near the center of the bull's eye. But however, if we work out the center of mass of this bullet holes, is here. So it's really not that bad. It's very close to the professionals. If given more and more bullets, or infinite number of bullets to this amateur, here are the results. So you can imagine that there are many bullet holes, but they can distribute it everywhere. Some could be very far away from even the target. But however, if we can work out the center mass or Gaussian center of all these bullet holes, we can see that it is very approaching to the center of bull's eye. So the result even much more precise than the professional's one single bullet result. So this example shows us why by collecting more photons could result in more precision in localization. And this is exactly what's going on in a single molecule based super resolution microscopy. Just now I showed you one of very simple case, which is one single molecule, and its image is an area disk, and the position of single molecule could be very precisely represented by the center of mass or Gaussian center of the area disk. So now let's look at a more complicated case. So instead of one single molecules, we have many single molecules, and the distance between neighboring single molecules are less than microscope resolution. So that means when we image them, and if each single molecule form area disk in the image forming planes, and these area disks would overlap each other. This is because their distance are less than the microscope's resolution. So in this case, when they form the image is going to be look like this. It's going to be a very hazy cloud. It's very hard to tell how many molecules are there inside. Of course, it is impossible to do Gaussian fitting, and it doesn't make any sense to do center mass fitting because we don't know how many molecules and what's the distribution of these single molecules contribute to this image. So this has been always a great challenge for single molecule based localization microscopy. So for the Palm and Storm, they use a very clever trick to solve this problem. The trick is, do not turn on all these molecules simultaneously. Instead, only turn on a selected site, a very small subset of these molecules to image them. And because very small number of these molecules are randomly turned on, this will make sure these turned on molecules are far away from each other so that they could be resolved, so that the area disks are not overlapping. So now let's introduce you what is Palm or Storm microscopy. So Palm stands for photoactivated localization microscopy, where Storm stands for stochastic optical reconstruction microscopy. So stochastic, that means random. So Palm and Storm, from technical point of view, they are slightly different, but they essentially use very simple principle. So in this lecture, I treat Palm and Storm interchangeably. So to be simple, I just use Palm to represent both Palm and Storm. So Palm uses very special fluorophores. So these fluorophores are either photoactivatable fluorescence protein or photoactivatable dyes. So photoactivatable fluorescence protein, also called PA fluorescence protein, for example PAGAP. So it's photoactivatable green fluorescence protein. So these proteins are very special, or these dyes are very special. So because their fluorescence could be turned on by activation beam. So activation beam actually is just activation light. For example, PAGAP. PAGAP is not a fluorescence protein after its synthesis. So this is a variant of green fluorescence protein. So this variance of green fluorescence protein after synthesis is still non-fluorescent protein. So non-fluorescent, that means if you shine with excitation light of GAP, there will be no emission light generated because it's non-fluorescent molecule. However, if you shine an activation beam for PAGAP, the activation beam is 405 nanometer. So this is a purple light or violet light. After shining this light, the PAGAP will undergo some changes, so now it will become fluorescent molecule. So that means now if we shine excitation light of GAP, there will be emission light of GAP to be generated. So now let's look at how does Palm work. So this is a cartoon to show how does Palm work. So imagine this is a part of cell. So these are the microtubule networks. So for this case, the microtubule is labeled by PAGAP. So there's a PAGAP genetically fused to tubulin, and this PAGAP transfected and then expressed in this cell, and PAGAP is expressed. This protein could substitute endogenous tubulin to be incorporated into microtubule network. So to call that PAGAP after synthesis, they are non-fluorescent, they are dark. So now if you shine excitation light, there will be no emission light generated. The cell is completely dark at this stage. Then at this stage, we shine on activation beam onto this cell. So the activation beam intensity is adjusted such that only very few PAGAPs are turned on. So this can be readily controlled by the intensity. So the less intensity, that means the less number of photons per area. So this less number of photons could be randomly absorbed by the PAGAP to convert PAGAP from inactive state to active state. So now let's assume these PAGAP molecules are activated. Now if we shine the GAP excitation light, there will be emission light generated. So this activated GAPs will generate single GAP molecule image. So the image will be area disks, and these area disks are far from each other, and they could be independently Gaussian fitted, or to obtain Gaussian center, or to obtain their center mass. So this center mass could be recorded, that will become this GAP molecules precise localization and nanometer resolution. So afterwards, since these GAP molecules have already been imaged, so we could photo bleach them to kill them. So they will become permanently dead. So in the next round, we're going to shine on the activation beam again, still at a very low intensity. So still, some PAGAPs are randomly or stochastically turned on. So these turned on molecules are very far away from each other. So their area disks are not overlapping. So we can Gaussian fit each area disk to obtain the precise localization of this set of PAGAP molecules. We can repeat this process again and again. For each repetition, we can get a set of molecules imaged. So if we add up all the molecules together, we can get a high resolution or super resolution image of PAGAP labeled microtubules. There is a very good online interactive animation to show the process of single molecule based super resolution microscopy. So here is a storm. So here at the beginning, here it goes. So at the beginning, this is photoactivatable fluorescence protein labeled microtubule network. So it's totally dark because without activation beam, these photoactivatable fluorescence protein are non-fluorescent. So now if you shine the excitation light, there will be no emission light coming out because these molecules are non-fluorescent. So now let's shine the activation beam. Okay, so we can control the activation beam with such a low intensity that only randomly certain PA fluorescent proteins are activated. For example, these molecules absorb the photon, activation beam photons, become activated. So these molecules now are fluorescent molecules. If we shine excitation light, for example green light here, there will be emission light coming out. So these are orange light. These are the emission. So this orange light, the image of these single molecules, these PA fluorescence proteins, are all area disks. So because the density are so low that these area disks are far away from each other, they do not overlap with each other. So each one could be treated individually, use Gaussian fitting or center mass fitting to obtain the center mass or Gaussian center. So these centers represent the precise localization of these single molecules by the aid of computer. So these centers will be recorded and stored inside the computer. And afterwards, these single molecules, these activated single molecules, which are fluorescent, will be photo bleached to all turn them off. So now the sample is dark again. So now enters a second cycle. So first we shine photo activation beam, then we use the excitation light to generate the image. Then we do the Gaussian fitting or center mass fitting to get the exact position of each single molecules. Then photo bleach these molecules. Then record down their precise XY location together with previous set. We repeat this process many times, so we can get a super resolution images with a nanometer resolution.